Hi everyone, thank you for joining today at AWM Pitt Grad Seminar. Today we have two speakers. Our first speaker name is Jenita Jahangir. She is a PhD student from University of Louisiana at Lafayette. And our second speaker is Rui Fang. She is a PhD student from University of Pittsburgh. The topic of our first speaker today is a discrete time stage structured model for host parasitoid interaction with pest control. And the topic of Rui Fang is today ensemble Monte Carlo penalty finite element method for the Navier-Stokes equation with random forcing and initial condition. So I would request Jenita Jahangir to proceed.
Okay, thank you, Farzana, to giving me the opportunity to share my research work with all of the people here. So I'm sharing my screen. I hope everybody can hear me and see my screen clearly.
Yes.
Yes.
Okay, so I'm Jenita Jahangir. I'm a mathematics PhD student in University of Louisiana at Lafayette. I'm going to present my research work, a discrete time stage structure model for the host parasitoid interaction with pest control. That's joint work with my supervisor, Dr. Amy Vepraskas. So you can see the map of United States. It's showing the agricultural production area. So the dark green area represents the major vegetable production area, and the light green area are the minor vegetable area. So from the picture, we can see we can say that the agriculture is one of the most important part for a country to develop. But in agriculture, one of the most important problem we face is crop pests. So my research is related to the crop pest, that is the host and parasitoid model, where host is considered as the crop pests. So here is the parasitoid. What is the parasitoid species? I will describe now. A parasitoid is a species that lays their egg inside of the body of the host, ultimately killing that host. The parasitoid offspring develop. So you can see from the first picture, the egg of the parasitoid is lying on the host. And in the second picture, you see that the parasitoid larvae are emerging from the body of the host. And the next, the big picture showing the adult parasitoid are parasitizing the aphid hosts. So the life cycle is of the parasitoid is like that. The parasitoid lays their eggs inside of the host. After hatching hatching the eggs, it needs some time to develop, and after the larval development, the body of the host become mummified, and after some metamorphosis, the parasitoid emerges from the body of the hosts. So the life cycle of the parasitoid mainly divided into two sections, the oviposition and the mummification, and mummification to emergence. And we are considering intraspecific competition. So that's for the food that reduces the growth and developmental reproductive rates in hosts. So one of our motivation from article in Stark et al, we see that they spray different type of pesticides to immature and mature parasitoid. And from the blue data, you can see these are the pupa survival rate after spraying pesticides, and the yellow data are representing the adult survival rate after pesticide spraying. So here we can clearly see that the adult parasitoid are more susceptible to the pesticide spray. Assumption, and our model assumes following order of events: parasitism, reproduction, death, and maturation. The host and parasitoid has two stages, juvenile and adult. The juvenile parasitoid grows inside the host, while the uh, adult parasitoid is outside the host. And only adult parasitoids are capable of attacking both juvenile and adult hosts. That's our assumptions. And here are some variables and parameters we used to formulate our model. So H1 describe juvenile host, H2 describe adult host, P1 describe juvenile parasitoid, P2 is adult parasitoids. Si is the survival probability, gamma I is the transition probability, and in beta I is the average number of viable parasitoid eggs. If 0 is host fecundity, AI is parasitoid searching efficiency. So we assume that adult parasitoids are capable of parasitizing the host. So here P2 represents the adult host. You can see the P2 is parasitizing H1 and H2. This red line represents the parasitism. So when H1 get parasitized by P2, they produced P1, that means parasitoid. And when H2 get parasitized by P2, that is parasitoid, so the host reproduces parasitoid. But when they are not parasitized, they produce the own species, like they produced hosts. And H1 develops to H2, that means the juvenile host matured into the adult host, and adult host reproduces. So that's the life cycle of the stage structure host parasitoid model. So these are our model equation. So in our model equation, this is the model is discrete time. So e to the power a2p2 negative a2p2 term represents the not parasitism. So and 1 minus e to the power negative a1p2 represent parasitisms. And in this model, we are assuming the host fecundity is satisfying the discrete time nonlinearity. So host fecundity is decreasing, and so that's our assumption here. So we analyze the model, and we find out the model has three equilibria: the extinction equilibrium, and parasitoid free equilibrium, and interior equilibrium. So we find out the inherent net reproductive number for the host, that is we denoted by R08, and the invasion net reproductive number for the parasitoid is given by like this. So our results are: the extinction equilibrium is globally asymptotically stable when the inherent net reproductive number is less than 1. The parasitoid free equilibrium of the model exists if the inherent net reproductive number is greater than 1, and is locally asymptotically stable if the invasion net reproductive number for the parasitoid is less than 1. So next result is we are assuming the inherent net reproductive number is greater than 1. That means we are assuming the parasitoid free equilibrium exists and is globally asymptotically stable in R4 except where the host density is 0. If the invasion net reproductive number is less than 1. And we find out interior equilibrium is locally asymptotically stable if the invasion net reproductive number is greater than but close to 1. We find out some numerical examples to demonstrate our analytical results. Like we find out some parameters that shows when the host fecundity is close to 6, all of the population goes to extinct. And we find out when the host fecundity is close to 60, so the host population persists, but the parasitoid population extinct. And when it is close to 600, so all of the population persists. Now we want to introduce a new parameter that is epsilon I, which incorporate which shows the combination of chemical control and biological control. So epsilon actually represents the mortality after spraying chemical exposure like toxic in a spray. So our model equation now change 1 minus epsilon 1, that is represents the survival rate after spraying chemical. So here we are assuming the order of events like parasitism, reproduction, death, maturation, and toxic exposure. So we are assuming we are spraying at the end of the time interval of the discrete time. So all of the model equation will remain same as our previous model, except we will just spray at the end and 1 minus epsilon I will be multiplied with the host equation, which is the survival rate after spraying toxicant. And here we are assuming the toxicant doesn't have any effect on the parasitoids. And our inherent net reproductive number and the invasion net reproductive number for the parasitoid will change accordingly, since we are assuming we are spraying toxicant at the end of the interval. So these are the expression for that. So now if we draw the bifurcation diagram with the parameter epsilon, that is our chemical spray, so we can see the host density is decreasing with the increasing of the toxicant spray, and the host density is dying at the end of the like when epsilon is sufficiently large. And since the parasitoid doesn't have any toxicant effect, still the parasitoid are dying because the host are affecting the parasitoids. So that's our required result. We want the host to die. So we are, for your information, I'm assuming here the epsilon 1, epsilon 2 is equal. That means the host, both stages has the same effect, like same chemical effect on them. Case 2, now we are spraying at the beginning of the time interval. Now the model equation changes, whenever we will find some hi, I will multiply with the 1 minus epsilon I. That means I'm spraying toxicant at the beginning. Then everything happens like parasitism, but death and maturation. So here you can see from the model equation that this equation is different from the previous, and 1 minus epsilon 2 represents the same survival after spraying toxicant spray, and this happens beginning of the time interval. So for that, the inherent net reproductive number of the host become like this, and invasion net reproductive number of the parasitoid is like that. So for your information, this R0P, that means invasion net reproductive number is smaller than the previous one.
Excuse me.
Mm-hmm.
Why was the P2 not affected by the toxicant in the last slide?
Because we are assuming parasitoid, like pesticide, are not affecting parasitoids. Like pesticide is not affecting the parasitoids. We are assuming in our model.
I see.
Like you can see from the previous one. So
Mhm.
here is also not parasitoid is not affecting by the pesticides.
Mhm.
So that's our assumption here.
So the goal of the toxicant is to kill the host.
Yes.
I see.
But we will see at the end what will happen if the toxicant affect the parasitoid. What will happen? We will see in a minute.
Okay.
Thank you. So that's the toxicant exposure at the beginning of the time unit. So we are seeing the invasion and inherent net reproductive number. And you can see if we draw the bifurcation diagram with the increasing of the epsilon, we see the host density is increasing at the beginning, and it started to decrease. So, and it goes to zero when like toxicant is very large. So, like if we spray at the beginning of the time interval, it become worse because our host density is increasing. Here, parasitoid is still decreasing. You can ask why it's decreasing, since the parasitoid doesn't have any chemical effect. Still, it's decreasing because the host is affecting the parasitoids. So we are now comparing different type of controls for the case 2. We can see here the blue line is only biological control, and this green line represents no control, and this pink line represents only pesticides control, and the red line represents both control. So only parasitoid control is doing a great job here. If we see like the both control, even the pesticide alone cannot do much because host density is bigger, you can see. But the thing is, by only parasitoid control, we cannot remove the host completely because we have to add some supplemental parasitoid to kill the hosts. So here we see that only parasitoid control is doing great job, but at the end, pesticides and like both control is killing the host, but not only parasitoid cannot be able to kill the host. So that's the thing. What happens if pesticide has effect on parasitoids? That's the question of for Anna. Like you can see this pink dot is like without pesticide effect on the parasitoid, but whenever you have the pesticide effect on the parasitoid, can you see that the host density is going much bigger? So if the parasitoid has a chemical effect, so the host density is getting bigger. So it's not good for us. We want the host to decrease. So in that case, the parasitoid is decreasing. So that's the graph related to your question. Now we want to extend the model to a periodic system by introducing periodic releases of parasitoid and pesticide spraying to the base model instead of spraying pesticide each time unit. Earlier, we are spraying pesticide every time you need. That's not actually reality. That's not real thing we can consider in our real life. So every day or every time interval you cannot spray. So now we are going to the reality and thinking that we are spraying some interval periodically. So we are spraying periodically, like every QK time unit, we are spraying, and you see the host is affecting the by the spray. See, this is the juvenile host, this is the um, adult host, and we are also assuming after like spraying, we are releasing some constant parasitoids to our fields. So this tau1 is the juvenile parasitoids, and tau2 is the adult parasitoids that we will release every QK time unit. So we are now analyzing the host eradication periodic model. So that's my results. The host-free system has a periodic solution, and for every solution, this system will very close to the periodic solution if the time goes to infinity. And the host eradication periodic solution of the system over the interval we are assuming QS plus and QS plus 1 is globally attracting if the spectral radius of this matrix is less than 1. So we find out some sufficient condition for that. So this is our sufficient condition.
What does a host-free model mean in this case, or why would we want that?
So in this model, there is no hosts.
So the parasite grows?
Only the parasite, yes.
Okay. But it needs a host.
We want to eradicate the host. So that's the host-free model.
I see. Okay. So once they're all gone, kind of. Okay, thanks.
So that's our numerical example. Our example shows that this Q is our frequency of toxicant spray, and tau2 is like the releasing of parasitoid. So if we draw this parameter Q tau2 plane, this shows that for the global stability part, the global attracting region that we got from our analysis result, we see that in this part, if it is less than 1, so this region is host eradicate. So in that part, there is no host. So if it is greater than 1, so we can see there is some blue lines, so blue data and this yellow data. So it represents the host is getting outbreak in this region. So we are finding some region there is host is totally eradicated, and some region that might have some host, and in some region there is host is outbreak. And that's our main results. So combination of different type of controls. So this red line represents when the parasitoid has the same effect, same pesticide effect as the host. So you can see when the parasitoid has the same pesticide effect, so host density is increasing, and it going down at the end of the time interval when epsilon is large enough. So here you can see this red line is representing the parasitoid density, and this pink line represents when the parasitoid has half effect as the host. Half effect means half pesticide effect. So so you can see it's become so stable, the host density, and at the end it's going to die. But when this blue line represents there is no pesticide effect on the parasitoids, so the host density is decreasing. That's our required part, right? So we want the host density to die. And you can see when the parasitoid has effects, so it's going down at 0.7, and when like more before than that, when it has effects on the parasitoids, so it's going down like 0.98, 97, going like down, and it goes extinct, and the host going extinct at 7 when the parasitoid doesn't has any effects. So you see at 7 the host dies. Why parasitoid is dying? Because the host is affecting the parasitoid. And when there is no host, parasitoid become stable because we are releasing parasitoid constantly. So that's why the parasitoid is constant in that line. So we can see from the results, like if parasitoid doesn't have any chemical effect, host density goes to extinct easily. But if the parasitoid has chemical effect, the host density getting larger for that. So that's our conclusion. We have analyzed the discrete time post-parasitoid model structure in both species. We incorporate continuous chemical control to the base model. We extended to this an impulsive difference equation with periodic spraying and parasitoid release. Next, we want to analyze the model with toxicant resistance and seasonality, potentiality applying optimal control to this. These are the references. I would like to thank my supervisor, Amy Vepraskas and Azmi Akli, for their support and guidance to my research, and the organizers of this seminar for the opportunity to share my work. And this work is supported by Louisiana Board of Regents Office of Sponsored Programs. Thank you, everyone.
Thank you
Any
so much.
questions?